Alright, tonight's live session we're going to be talking about average rates of change along with transformations of functions. So I'm going to go ahead and get started here. So first off, there's a lot of questions in terms of what does the average rate of change of a function f of x over the interval a, b tell us about the function? What the heck does this stuff mean? Well, it seems real complicated. You see this average rate of change and all that jazz. And the function f of x, that can be any function, and then this interval a, b, it can be any numbers plugged in. But essentially, what we're looking at is you have a couple of function values, and we'll just call them in general a and b. And so, if this function's f of x, what happens is, if this is a for your x value, that means the y value corresponding to that point has to be when we plug in for x in the function value. So this y value right here corresponds to f of a. Or you could just say the point is a comma f of a. In the similar manner, we can take b, and we know that we're plugging it into the function, and we should get some corresponding y value. Excuse that a f of a right there, but you get f of b for the corresponding y value of that. So this is b f of b. And so what average rate of change is actually asking us to do is just find the slope of a line. So the average rate of change of f of x over the interval ab is just equal to the slope of the line from a f of a to b f of b. So what that means at the end of the day is we get this equals, well, how do we find slope between 2 points? You just do the y2 minus y1 divided by x2 minus x1. Well, our y2 would be f of b minus f of a. That's our y1. All over it. Now we have to be consistent. Since y2 is f of b, that means our x2 is b and our x1 is a. So, and I'm going to abbreviate this. This AROC is the average rate of change. That's all it is. It's just a slope of a line. Every time you're finding the slope of some line, and the way we find which line we're working with, it's the interval. You plug in those x values into the function. That's it. Every single time works out nicely. So that's what I want to see if we can do here. And you don't even need a graph to do this. That's the beautiful thing here. So if we have a function, f of x equals 2x squared minus 7x plus 3, and you have some given interval. Let's say our interval is 2, 5. So what that means is we need to find 2 points. Alright? And so if 2, this is our x1, and this will be our x2 value, we need to find what f of x1 and f of x2 is, because that'll be our y value. So essentially our y1 is equal to f of 2, which equals, well, f of 2. Now here's the tricky part for some people, but notice we have f of x. So there's an x here, but that means we got to put an x in for that x in those two positions. So we get 2 times, and I'll put it in parentheses, 2 squared minus 7 times 2 plus 3. Okay, so let's figure that out. Well, 2 times 2 squared is 4, and then multiplied by 2 is 8. So you have 8 minus 14 plus 3. So 8 minus 14 is negative 6, plus another 3 should be negative 3. So that means our first point would be 2 comma negative 3. As for our second point, our y2, essentially, that has to come from f of 5, because 5 is our x2 coordinate. And moving forward on that, what do we have? Well, we have 2 times 5 squared. Remember, 5 is replacing the x values once again. And so minus 7, there was another x there, so we'll replace that with 5. And then plus a 3. So notice 5 squared is 25, multiplied by 2 is 50, minus 35 is 7 times 5, plus 3. So 50 minus 35 is 15, plus another 3 is 18. So for our second coordinate, we get 5, 18. So now the average rate of change over this interval is 18 minus negative 3, all divided by 5 minus 2. In other words, we have 21 over 3, and so our average rate of change is 7. We can do something similar for our next case here. And just to kind of give you a different flavor, you could do the same song and dance where we find those 2 points and then just find the slope of that line containing those 2 points. Or the formula that we found on the previous slide there. Remember, it goes f of b minus f of a. So if I go f of 3 minus f of negative 1, then down below I just need to line things up. I go 3 minus negative 1. Okay, so what is f of 3? So this is a slightly different arrangement as to what we had before, but remember, it's still just the slope of a line. So if you prefer using just the 2 points, fine, use that. But so now working this one out, notice f of 3, I'll put it all in parentheses for f of 3. And then we'll do the same thing, all in parentheses for f of negative 1. And we'll still have the 3 minus negative 1. And I'll kind of line those up just so we can see what's happening. So f of 3, let's figure out what that is. So we're going to replace all the x's with 3. So we have 2 times, once again, 3 squared, minus 7 times 3, and then plus 3. And then for the negative 1, remember we're going to replace every x value with negative 1. So every x value up at the top has to be replaced with negative 1. So you get 2 times negative 1 squared minus 7 times negative 1 plus 3. Now, since we're subtracting all f of negative 1, notice how that second piece was all in parentheses. That's because we had to distribute that minus sign. So if you're going to use a shortcut, just be careful when you're using it. That's all that I ask. Another method, what we could have done is we could have found f of 3 first. By the way, so you could have written 2 times 3 squared minus 7 times 3 plus 3, and then found f of negative 1, which is 2 times negative 1 squared minus 7 times negative 1 plus 3, and just found out what they equal. But what you'll notice actually, one thing that's kind of nice here, is that certain terms start to go away right out the gate. So we'll go through both methods to find the answer. So 2 times 3 squared, so 3 squared is 18, minus 21, so that makes negative 3 is what's left over in the first term. And then 2 times negative 1 squared is 1, so 2 times 1 is 2. And then minus 7 times negative 1, that'll become plus 7. So that'll be, so 2 plus 7. And remember, we're subtracting all this, so subtracting 9. And then all of this is over 4. Okay, so notice this makes, let's see if we can fit it in here, negative 12 over 4, which is equal to negative 3. And if we would have done it the longer way, not canceling out the 3's, notice in the first case you get 9 times 2 is 18, minus 21 is negative 3, plus 3 makes 0. Okay, and then on our second one we have 2 times negative 1 squared, negative 1 squared is 1, times 2 is 2, plus 7 is 9, plus another 3 makes 12. Okay, and notice if you subtract those two you get negative 12, and then divided by the 4, and that's how you get your answer of negative 3 once again. So a couple different ways to get the same answer. Now moving forward to the next one, average rate of change. We can do f of 6 minus f of 0 all over 6 minus 0. So pick your favorite method. You've seen a few different ones. This one I will work off on the side first just so you can see it that way completely worked out. f of 6, once again, equals 2 times 6 squared minus 7 times 6 plus 3, plus 3, there we go. So 6 squared is 36 times 2 makes 72. So 72 minus 7 times 6 is 42 plus 3. So that'll be 30 plus another 3 makes 33. F of 0, luckily this will be a nice easy one for us to work with. This is 2 times 0 squared. We're replacing all the x's once again. Minus 7 times 0 plus 3. Notice everything's 0 except for that constant term, so our answer is just 3. Okay, so we have 33 minus 3 all over 6 minus 0. And so that makes 30 divided by 6, which gives us a final answer of just 5. Notice in this case, all of our answers came out to be some nice round number. So does that always happen? Well, the answer is no. You can have fractions as well. These actually have a special property, which we'll kind of refer to a little bit later. And it ties in with some discussions that we've had before. So let's take a look at another problem where we don't get those nice sort of answers. So in terms of these, we got a new function here. So we need an average rate of change. And in this case, we'll do g of 3 minus g of 1 all over 3 minus 1. Okay, that's the average rate of change because that's the interval. And however you kind of prefer, I'll do one of the last two methods to start. So g of 3. Now we got to plug in for all the x's. So I'll kind of circle up here. You have an x right in here. That's going to be replaced with the 3's. And then we have two x's in those two positions. So we get 2 times 3 minus 3 all over 4 minus 3. So notice 2 times 3, 6 minus 3. So I'll write this out for now. 6 minus 3 over 4 minus 3 is just 1. So that's just going to equal 3. And g of 0 equals 2 times 0 minus 3 all over 4 minus 0. And so what do we get? We get negative 3 up top and 4 on the bottom. So negative 3/4. So this is not going to be a nice round number anymore. So we get 3 minus a negative 3/4 all over 2. Okay, and so this actually becomes, to make it a little bit nicer, 3 plus 3/4 all over 2. And we could do this a couple ways. You could get a common denominator in the numerator, then kind of do this keep it, change it, flip it rule. An easier method that I'd recommend is just notice the denominator is 4. So we'll multiply both the denominator and numerator by 4, so that'll make our lives a little bit easier. So what happens is the denominator, that's easy, it becomes 8. So 4 will have to distribute to both of these terms. So 4 times 3 gives us 12, and then 4 times 3/4, the 4's would cancel and leave you with 3. So you get 12 plus 3 all over 8. So it's going to be 15 over 8. Okay, and that's a good final answer right there. Alright, moving forward to our next one. This one will be even nastier than the ones before it. So in this case, what do we have? Well, we have g of 8 minus g of 5 all over 8 minus 5. Okay, so how does this thing look? Well, notice we'll have right out the gate, we'll just plug them in. We're just replacing the x values, so we get 2 times 8 minus 5, or 8 minus 5, I'm sorry. 2 times 8 minus 3 in the numerator, then 4 minus 8 in the denominator. Then we have to subtract off this g of 5, so the 5 gives us 2 times 5 minus 3 in the numerator, all over 4 minus 5 in the denominator. And now we're having the 8 minus 5 down below that we needed. So what does this become? Well, 2 times 8 is 16, minus 3 is 13, and then 4 minus 8 makes negative 4, so we're left with that. And then on the other case, we have 2 times 5, that's 10, minus 3 is 7, all over negative 1. And then all of this is all over 3. So simplifying a bit further, notice we have a negative and a negative in that last scenario. So we have 13, and let me just pull that negative symbol out in front, negative 13 over 4, then it becomes plus 7 all over 3. So notice once again, in this case, we have 4 as our magical denominator that we're dealing with. So we'll kind of try and break that on down in the numerator there. So let's multiply by 4 over 4. Okay, and remember we're going to have to distribute that to both terms. So this whole thing equals, notice we'll have a negative 13 in the first case. 7 times 4 makes 28 in that second case. 3 times 4 makes 12. So this becomes 28 minus 13 is 15 over 12. Now you have a common term in there, so both of those are divisible by 3. So we could divide both out by 3, and then you have 15 over 12 becomes 5 over 4. And that's a good final answer for us. So hopefully we see how these average rates of change are coming about. And if you have any questions, as I said, post them in the chat box. I'm happy to answer them along the way. Alright, so what do we want to look at in general? Well, ideally, all these, if you recall what the average rate of change is, this is the slope of the line between 2 points. And that line, having 2 points on the curve, is called a secant line. And ideally what we want to do is build to this idea of a tangent line, and that's a big idea for us. And so I'm not saying this is necessarily to scale. As a matter of fact, I can find out if it is. Let's say we wanted to go how this function f of x equals x squared minus 6x plus 8 varies from 5 to 5 plus h. First off, I can find what f of 5 is. And I'm going to have to use this anyways later on down the road. So 5 squared minus 6 times 5. Well, let me put that 5 in parentheses. It's not necessary to put it in parentheses in this case, but it's just good practice to get into. So f of 5, you get 5 squared minus 6 times 5 plus 8, so that should be 25 minus 30 plus 8. And 25 minus 30 is negative 5, plus 8 makes positive 3. So hopefully, if I've drawn this correct, this 5 should line up kind of right with this 3, and it does actually. So this is 5, and that's 3. So the coordinates of this point is 5, 3. And what we want to start to do is start to create different points at different lengths. And on the other side too. So I could look at a secant line of this type. And then I could look at another secant line. Say more on this side of this type. And then we could look at another secant line and have it be really close. I'm not saying that's to scale at all, but what you're seeing is we're getting closer and closer to that point every time. And so what happens is, rather, with the 5 being fixed, it might be easier for us to shift our notion. And so I could go on either side, by the way. I was going from the left, I could have done from the right too. If I go from the right, I get a line like this. In general, if we have some 5, we can look at some of 5 plus h, where h can range to any other value, whether it's positive or negative. And if we can find that average rate of change, we're going to be in good shape. And the trick to that is, if we can find f of 5 plus h, what the heck does that equal? Well, f of 5 plus h, now notice, we've replaced every x, and so we've replaced this x. Now we're going to replace this x with 5 plus h, and then this x with 5 plus h, and see what happens. So we get 5 plus h, the quantity squared, minus 6 times the quantity 5 plus h. and then plus 8. And this gives us a point that we're going to be working with. And so what happens is we get, if you remember your polynomial formula, your expansion formula of a square, this becomes 25 plus 10h plus h squared. If not, just write it as 5 plus h times the quantity 5 plus h. And then minus 6 times 5, remember we're going to have to distribute this 6 to both terms. So minus 30 and then minus 6 times h right there. And then plus 8. So 25 minus 30 plus 8 we already talked about. That's going to be a positive 3 at the end. And we'll have an h squared right in the front. We'll put that. 10h and minus 6h. That should make plus 4h. And so then we have plus 3. Okay? So now, if we want to find the average rate of change over this interval, what happens? Well, we want to find f of 5 plus h minus f of 5 all over 5 plus h minus 5. And I'll put the 5 plus h and the minus 5 here in parentheses. So what's f of 5 plus h? Well, we just found that. That's h squared plus 4h plus 3 minus, and just to go back to the standard color here, f of 5 we found was 3 all over 5 plus h minus 5. That just becomes h. So notice what happens. The 3's cancel, and we get an average rate of change of h squared plus 4h all over h. And if we wanted to get fancy with it, we could factor out an h in the numerator, and you'd be left with h plus 4 divided by h. And you could say your h's cancel with the exception of, so this h would cancel with this h, except h cannot equal 0. So what happens is this whole quantity becomes h plus 4, where h does not equal 0 because h was in the denominator at one point, and we can't divide by 0. Okay, so whoopity-doo, right? So how we can use this is to find the average rate of change from 5 to some other point. Find the average rate of change of f of x over the given intervals. So before we had to plug it in all the time, right? So if we have, let's say, one endpoint, now it has to be fixed at 5. So one of these endpoints always has to be 5. So let's say 5 to, the first one goes to 6. And in the second one, we'll go, say, 5 to 5.1. So in 5 to 6 on that interval, notice what we've done. Well, 5, if 5 plus h equals 6, so 5 plus h is this point, what we have is h equals 1. Right? So what that means, we've already got a formula for it. It's h plus 4. So the average rate of change, and you could test it, actually go the long way, but we could just plug in 1 for the h value and get 1 plus 4, your answer is 5. Done. In our next case, if we have 5 plus h equal that second coordinate, because 5 is fixed there, that means h equals 0.1. So in that case, the average rate of change equals, well, it should be 0.1 plus 4 according to the formula that we just found, and so it's 4.1. And notice what's happening is our interval is getting closer and closer to 5 between these, and as a matter of fact, you have these questions of tangent lines. Tangent lines only touch the curve at one point, so they'd only hit this curve at, say, 5,3, and so you'd have a curve that basically just kind of goes right along it, but never touches it except for that 1.53. And the slope of this line even though we can't plug in h equals 0, that's basically what we want. So the slope of this line happens to be 4. And if you decide to go on and take, say, pre-calculus or a calculus course, you'll actually work on this stuff all the time. It's called an instantaneous rate of change rather than an average rate of change. That's the idea that you're building towards there. So hopefully that kind of tells you where the average rate of change, where you can go with it. So a little bit more complicated example, but that's all you're doing is just another average rate of change formula. So, all right, don't see any questions at this point, so I'll keep on moving along into transformations of functions. So transformations of functions, they can be a little bit tricky at times, so we'll try and work and see what happens with this. So the 4 main transformations that we're going to deal with, these are all going to be, to start I should say, are shifts. And what does that mean? Well, we're either going to do what's called a vertical shift or a horizontal shift when you see a plus or minus k where it's not multiplication. It's just addition or subtraction involved with our function. So I have a function over here, f of x equals x squared, and I'm going to do some simple shifts. So I want to mimic this f of x plus k where k is greater than 0. So let's say we wanted k to be equal to 1. So what happens is, if k equals 1, let's say this is g1 of x equals x squared plus 1. What happens with the curve? This is going to be 1 unit. This distance here, it might not seem like it, is also 1 unit. And anywhere I go on the curve, I've just shifted the graph up 1 unit. And in general, what this does is f of x plus k is shifts f of x up k units. Okay? And so everything there, as you notice, we just kind of shifted the graph up 1 unit. And so we could try another graph. So let's see what happens when we go minus k. What does that thing look like? Well, so we'll pretend we shift down 2 units. And now I know I don't have all the tick marks and all that stuff, but I'm just trying to illustrate what's going on here with the curve. Kind of going on at the same rate. So let's say this is g2 of x equal to x squared minus 2. So what would happen with our graph? Well, notice you'd start at 0, 0, you shift down 2 units because you plug in 0, you get negative 2. So this is 2 units for our distance here. And anywhere you go on the curve, regardless, is all the same length. So 2 units there, and so on and so forth. So what's happened in general is if you have an f of x minus k, and I'm saying where k is greater than 0, so that when you're minusing k, it isn't a negative and a negative, is basically what we're trying to avoid. So this just shifts f of x down k units. Okay? Another graph that we can look at. If we go f of x minus k. So notice, let's say we went f of x minus 3 in this case. So that would be, what does f of x minus 3 in this case look like? So f of x minus 3 would become x minus 3, the quantity squared. The reason why we're replacing the x with this x minus 3 now. Okay? So with our graph, what happens is when you plug in 3, you should get 0. So we plug in 3 wherever that occurs. We'll say right around this space right here. We get 0. So what's happened with the original graph? Well, what's happened is, first off, we'll draw this line right here. This distance is 3 units. But also, this distance is 3 units. And this distance is 3 units. Right? And no matter where we go, we've just shifted the graph. And notice, which direction are we going? From the original, we always seem to be going in that right direction. So this shifts f of x right k units. And this can trip up quite a few people. Why so? Because you have a minus sign in there. It does kind of the opposite of what you would anticipate, I guess, is what we should say. And in our final case, I'm not going to bother to draw a graph here, but what happens in general when we go plus k? Well, if the minus sign shifts it right k units, you can take a wild guess. Notice we're inside the parentheses, and what happens is that we shift f of x left k units. And if you're wanting to see that, my suggestion would be is graph f of x plus 4, and that should equal, by the way, x plus 4, the quantity squared. And you'll notice right out the gate, negative 4 should give you 0 as an answer there. Oh, I forgot to write out what that was. So the g3 of x, sorry, up here, equals x minus 3 squared. That would be an example. So now, what we want to do is combine these ideas to write a formula for the function obtained when the graph f of x equals 1 over x is shifted down 4 units. So shifted down 4 units. And then to the right 3 units. So down 4 units, and we'll call this first like kind of shift along the way. What happens? H of x. Well, what do? If we want to shift down 4 units, which one of these follows the down 4 units? So we go right in this little slot right here. So shifting down 4 units would correspond to us going f of x, and instead of k units we have 4, so we'll put 4. So now, that was step 1. Now our next thing in the order given is to the right 3 units. So what we'll need to do now, instead of taking f of x, we need to take h of x and do something to it. So for our step 2, notice what do we want to do? We want to go to the right 3 units. So what are we going to look at? Well, shifting right 3 units corresponds to us taking this graph. Now we've replaced f though. F is now h essentially. H is our new graph. So the way to go about this is h of, well, we want x minus whatever the number is. So x minus 3. Okay. Well, h of x minus 3 is essentially f of x minus 3 minus 4. And what's f of x minus 3? That's the last trick, is we're plugging in for that x with x minus 3 now. So that's our magical value. So you get 1 over x minus 3 minus 4. And we could call this our new function, let's say g of x. Now a lot of people don't like to write out these step by step, and that's fine. Do it whatever works for you. But just kind of seeing how they go from one piece to the next, that's how you can build those functions at any point in time. Because they do get a little bit more complicated, and I'll kind of illustrate that with our next example. So now we're going to have 2 scenarios. We're going to have where k is greater than 1 and c is between 0 and 1. But before we even get to those good old examples, if we have g1 of x equal negative f of x, notice, what does that mean? Well, if g1 of x equals negative f of x, if we have our graph here being square root of x, this would be negative square root of x. So what happens to our graph then? Well, notice when we had positive 1 as an output, that would now become negative 1. When we had positive 2 as the output for 4, this would be 4 giving us negative 2. And same thing when 3 was the output for 9, we should correspond to negative 3. So what actually happened with this graph here? Well, this is, if this is g1 of x equaling negative square root of x, notice it seems like we've reflected over this axis, and that's exactly what we have done. And so anytime you have negative f of x, the general rule applies that you reflect f of x over the x-axis. Okay, so let's try one with g2 of x. So that's f of negative x now. But notice x is inside the square root, so we want square root of negative x. So what happens there? Well, notice you can't have all of a sudden square root of, if I plug in 1, I get square root of negative 1. That's undefined in the real numbers. You have to go to the imaginaries to get there. So that won't quite work. So the only types of numbers we can plug in are negative numbers. So notice if I plug in negative 1, I get negative, negative 1. And so that would be positive 1. So you get that point right there. The next one, if you plug in negative, negative 4, you get square root of 4 essentially, which is 2. So we get something like this. And notice, oops. What's happening to this curve? Well, it looks like this has been reflected. Our original graph has been reflected over the y-axis, and that's exactly what happens when that negative appears on the inside. So, and notice we aren't subtracting, we're multiplying the x by the negative. So this is reflect f of x over the y-axis. Okay, so now let's see what happens. Let's look at some other types of things. So notice our next one talks about k times f of x. So let's have g3 of x. We want k to be some number bigger than 1. So we'll go 2 times f of x, which is just square root of x. Or I'll write out 2 times f of x for now. And that's 2 times square root of x. So what happens to our original graph? Well, notice we've multiplied by 2 everywhere. So all of our values, when you have 2, you'll double to 4. When you have 3, you double to, say, 6. So 1, 2, 3, 4, 5, and I'll put up a 6 value there. And so now you might think this is a vertical shift. We haven't done a vertical shift because notice at 0, we haven't shifted at all. But it seems like if you notice our distance, here it's 1 unit. Here it's, our distance apart is 2 units. Our distance apart here is 3 units. And what is this, though? If you notice to our axis, this is 3 units. This is 2 units. And this is 1 unit. So basically, given any value, we've doubled it, right? And that makes sense. And the way we actually write this is a vertical stretch. So this is a vertical stretch of f of x away from the x-axis by a factor of, well, what were we doing every time? Well, we multiply by 2 essentially. So in general, it'll be by a factor of k. In a similar manner, I'll put it without showing you the graph. You can try this on here. If we had this value be, say, 1/2, notice it's going to go in the other direction towards the x-axis. And so what we call that is a vertical compression. Of f of x toward the x-axis by a factor of c. Okay, so let's try one more here. Let's see what orange looks like. So we'll go to g5 of x. So if we take g5 and let's say that we have this be 4, so f of 4x, notice that would equal the square root of 4x, right? And when you think about this, what's going to happen? Well, if we've done things right, we can start plugging in values. And notice, if you're wanting, say, when we plug in 1, what happens? Well, 1 gives you 2, right? And where would we get 3 at? Well, that's when we need some fraction here that would make 9, so that would be 9/4 essentially. So it's somewhere a little bit beyond 2, so something like this. And what actually happens, to be honest with you, is you get this graph right here. You might say, well, wait a second, how do we, that's not a vertical stretch. And the idea is, you could think of it as a vertical stretch in some regards for this case, not always, but the way we can actually think about this one, and by the way, if you wanted to look, when x equals 1/4, what do we get? We got square root of 4 times 1/4, and that was equal to 1. And we can look at this distance here. So this distance here was 1 unit. And this distance here was essentially 4 units if we overlapped all the way to the beginning. Same thing here, you had 1 unit at this point, for the whole distance, but the distance from this point to the axis there, we just found was 1/4. So 1/4, if you notice, we're multiplying by 4 to go the other way. Our new curve is 1/4, and then we have 1 unit where it should have been 4 units in our original graph. So it's doing just the opposite effect of what we'd anticipate, and just kind of how the horizontal shifts were kind of going in the opposite direction. This is a horizontal compression. Towards the y-axis by a factor of, and notice we were multiplying by 4 inside, so but 1/4 showed up as our multiplier, so that's what we're compressing by every time. And in a similar manner, we can do the cx. Instead of being a compression, this is going to be a horizontal stretch. Away from the y-axis. By a factor of 1/c. So now we have all our values kind of in place, and we can start to do something with this stuff. So we have reflections, we have stretches, we have compressions, we have shifts, both horizontal and vertical. So with all that in place, we can actually start to tell what the graph is going to do. So describe how we have the graph of each function given as a transformation of the graph of the original function. So notice we have two things here. This f of negative x, so let's say we started with f of x. If we made our move to f of negative x, what do we do? Well, in that process, this is a reflection. Now over what? Well, notice the negative's on the inside, so if you take a look, we'll go one step back real quick. So f of negative x, reflect f of x over the y-axis. So reflection over the y-axis. Now, moving from here, where do we go? Well, we go 3 times f of negative x. Well, what does that do? Well, notice that this step, what we were doing right here, is basically just a vertical stretch. If you don't believe me, you can go back in your notes. So this is a vertical stretch away from the x-axis. By a factor of 3. And that's how we finished with our original function. So what we've done is describe how the graph of each function is the transformation of the graph of the original function. Take f of x, reflect it over the y-axis, then stretch the resulting graph away from the y-axis, or from the x-axis, my apologies there, by a factor of 3. So it doesn't matter what our graph looked like, we can always end up with our finished product of our graph. So let's take a look at our next one, see what happens. So we want to begin with some f of x. What's the first thing that we can do? Well, it's not going to matter too much on our order, but hopefully we can take care of that 6x. What does that do? Since that's on the inside of our parentheses here, this is a horizontal. Now you got to remember it's a compression. So compression toward the y-axis. By a factor of 1/6. Then all we do is we take that graph and we add 9. So that was this step. So what does that do? Well, that's just a vertical shift. And so now we're ready to write up what we're doing. We're taking f of x, compress toward the y-axis by a factor of 1/6. And then shift the graph up 9 units. Okay, so with all these pieces in place, we see how to work with that. What we want to try and do is see if we can graph this stuff. And if we want to be able to graph this, and without a calculator too, we have to know some basic graphs. So the graphs you want to probably know are the graph of y equals x, the graph of y equals x squared, the y equals x cubed, y equals 1 over x, y equals square root of x, y equals cube root of x, things of that nature. If you have most of those down, you should be in pretty good shape in terms of all the transformations, how this works. So what we'll do, we'll start off with a kind of a golden graph. Now, what do I mean by that? X cubed is what this seems to look like, because we have an x and a cube is our power here. So what we'll do is we'll kind of draw out the cube, how that looks. And I'm actually marking more points, sometimes a little more general, 3, 4, 5, 6, 7, 8. This thing goes up fast, so 2, 3, 4, 5, 6, 7, 8. lost my line there on the way up. Alright. So this is our graph of, we'll call this function f of x. Equals x cubed. Okay, so we want to do stuff to this, right? And so what's the first thing that we want to do? Well, we want to try and get this into 1/4 x cubed. So the way we'll do that is take f of 1/4 x, and notice that should equal 1/4 x, the quantity cubed, which is exactly what we want. Now what does this do? This becomes a horizontal, notice our c values between 0 and 1, and it's on the inside of parentheses. This is the horizontal stretch away from the x-axis or not x-axis, my apologies, the y-axis, by a factor of, well, it'd be 1 divided by 1/4, and that becomes, so a factor of 1 divided by 1/4 is just 4. So with that in mind, if you have this distance right here being, essentially we have that distance right there being 1, so that means we'd have to go 4 for that. And then when this distance is 2, that means we'll have to go 8 for that, because we have to multiply by 4 every time. So let's see, 3, there's 4, 5, 6, 7, 8. Okay. And in a similar manner, we can do that on the negative side. So if this distance is 1, we have to go 4 units. So we'll go out here. And if this distance is 2, that means we'll have to go 8. So 5, 6, 7, 8. And now we're kind of ready to draw our graph. Okay, and I'll erase that little purple line. Oops, put the black back in there. Okay. So I think we're finally ready for what our finished product looks like. What does this plus 1 do? Well, let's call this graph, let's say g of x. If we want to do q of x, notice all we need to do is take g of x and then we add 1, right? Because that would be, we get the g of x is 1/4 x, that quantity cubed, plus 1, right? So what does this do? This shifts g of x up 1 unit. And by the way, g of x was equal to 1/4 x, the quantity cubed. So everywhere we go, we're going to just shift up 1 unit. So we go right here, we'll shift up 1 unit. We go right there, we'll shift up 1 unit. We'll go right to this point and we'll shift up the 1 unit. That's supposed to be a little bit more to scale. Shift up here, we get up 1 unit. Shift here, we go up 1 unit. And if we've done this right, everything on our graph should be just shifted up. And this is our graph of q of x equals 1/4 x, the quantity cubed, plus 1. And notice we haven't used a calculator at all. Everything's just based upon transformations of graphs. And that's the beautiful thing, the reason why we try and pay close attention to this stuff. So if you have any questions in the meantime, just post them in the discussion board or send me an email or whatnot and let me know, and I'll set that up for the next session. Hope you all have a great night.